organizers for inviting me. This is my honor, both as incoming president of ARMA, as well as a fellow Canadian who has been living in the US for quite a while, to come back my hometown and greet this important initiative and effort. And congratulations to the student organizer, particularly the folks in this seminar who successfully kicked off the first ARMA student chapter in Canada. It's certainly not the last. I'm also very glad to see quite a few folks in the audience, including my old friends, for instance, Professor Rick Chaltanik from University of Alberta, as well as Yung Sheng, my old Waterloo buddy. And I can't be more thrilled to be in today's chat. It's kind of refreshing because I was chatting with the students before the talk, before we start. I told them that I miss so much of the good food in Toronto. And as a matter of fact, one of my most favorite activity that I vividly remember and cherish all the time is the Central Island in Toronto. I remember last time when I went back to Canada, I missed it so much. So after plane landed in the airport, I went to the Central Island, took the ferry, and just lying down on the grass, enjoy the sunshine. Having said that, I think today I also wear two other hats. One is as the incoming president of ARMA, to congratulate the students for these efforts, as well as encourage all the students and my Canadian fellows to continue supporting ARMA, supporting rock mechanics and geomechanics in general. We are relatively speaking, we are a small community, but very tight. And we're close to each other. You will find out very soon, especially for the students in the next probably 20, 30, or 40 years, you will find many familiar faces like Rick. I met Professor Rick Chaltanik a long time ago. And also I need to acknowledge Professor Giovanni Grasselli for not only helping sponsoring the student chapter, but also Professor Grasselli is key organizing committee member for our many ARMA initiatives, including International Geomechanics Symposia. So the success of that series has everything to do with dedicated organizing committee member like Professor Grasselli. So speaking of ARMA, Ali already mentioned a few highlights. I just want to add a couple more.
I'm sorry to interrupt. Yeah, thank you. I just want to make sure you're in presentation mode. Thank you.
Yes. So ARMA members is, as the incoming president, which next month become the president, I always ask, the first question always is what we can do for ARMA members. This slide is for ARMA general members. The next slide is about what we can do for student members. So that question I pose to the board, to all the volunteers, as well as the students too. So we need your advice. What you want, that's what we need to provide. So here is a list of what we do. For instance, many of you participated in this annual symposium just finished a couple of weeks ago. The first virtual symposium, very successful. 450 presentations. It's amazing, 75 sessions. Then we organize many workshops, short courses, training sessions, and focused topical forums. We have 5 technical committees, including Technical Committee on Hydraulic Fracturing, which I will highlight some of the work of what that committee has been doing. Induced seismicity, drilling, underground storage and utilization, which also includes CO2 sequestration, as well as turnover. We also, probably one key task or mission ARMA has been undertaking is to support and encourage students and early year career participants. So I will lay out the details in the next slide. We also, another thing, issue annual awards. I strongly encourage all students to participate in this, including research, applied research, case study, and PhD thesis and master student thesis. Those are all open for both career geomechanics folks as well as students, especially the last 2 PhD and master students. The award recipients are all from students like yourself. Feel free to participate. We also open another service category called the Outstanding Service Award. So those for the volunteers, like a student volunteer yourself, in the 3 categories: senior volunteer, a distinguished volunteer award for senior members, junior members, and student members. So there is a dedicated category for student alone for service award. All the student organizers are more than welcome to participate in this award opportunity. ARMA also publish letters you may receive. Also, all the ARMA publications is in one page, as well as online on the website. Last but not least, we maintain ARMA membership in the International Society of Rock Mechanics. What we can do for the students? That is question today. If nothing else you take away, especially for students, is this question. We need your help to make suggestions to ARMA what we can do for you to help you reach your goal. I'm so glad Ali mentioned several goals, purpose of this exciting chapter. So what ARMA as an organization can help you achieve those goals? Feel free to suggest. And those student chapters, we have 14, and they organize many different activities. Those activities all come from students themselves. Okay, it is not ARMA telling students what they need to do. It's the other way around. It's the students who tell ARMA, hey, we want, for instance, a student design competition. Can you help us? Therefore, ARMA provides assistance from judges, from sponsorship to support this. And Itasca, in this case, is a sponsoring company. And with 40 teams from 29 universities in 17 countries, this is the first student design competition. And this number is just mind-blowing. It's just simply mind-blowing. Shows enthusiasm as well as strong participations from all over the world. So in the future, you take over. For instance, there is another competition at the Annual Symposium for the research. A lot of students, including yourself, doing a fantastic research. So by showcase those research, and students compete with each other, and the winner For instance, in this case, is from a university, Texas A&M. Right, but having said that, you see the first design competition, the 3 schools from these 40 teams, one from University Columbia. This number 1. Number 2 is from Canada, Laval University, and number 3 from India Institute of Technology. And today I also noticed in the chat window, we have a representative from the University of Columbia participating in this talk as well. So those are all from students. And the treasurer mentioned the ARMA Toronto Student Chapter has not had a lot of financial fund yet. This could be your opportunity to not only win prestigious award, but also have some fun with other students. The third competition student organized is a photo competition. This is very refreshing from University of Monash in Australia. The organizers, student chapter organizers, putting together this program. ARMA provided the financial resources as well as the judges, as you can see, from all over places, from UK, US, and UAE, as the judges volunteer at this event. And the photos are just mind-blowing, okay? So those are the student activities. And I strongly encourage everyone in today's seminar, especially students, feel free to come up with your initiatives, your ideas, not only participate in those, but also suggest future activities you want to see. And at the symposium, for instance, I see one of the goals Ali mentioned is professional networking. At the symposium, thanks to student organizers from Texas schools, the students organized the so-called mentor-student networking. So this activity, ARMA helped put together 20 plus industry and academia senior members, including our fellows, ARMA fellows, network with the students. So each of the fellows talked with a group of students at the symposium through the online chat rooms. So those all come from the students. I strongly encourage you. Next, I would love to see what's come from University of Toronto. We are enabler. You need any resources, we will help you to achieve that. Okay. So I use the example of this slide as an example to show what the technical committee is all about. Because fundamentally, ARMA is technical community. Okay, technical excellence is our foundation. So for the technical committee on hydraulic fracturing, for instance, is leading a community called hydraulic fracturing community. Right now, as Ali mentioned, we are we are the largest technical society on this topic in the world. And over the years, each year we organize an annual workshop. And over the years, it grew so much, we changed the annual workshop to an International Geomechanics Symposia. And Professor Giovanni Grasselli has been helping organize as well. University of Toronto has been one of the key supporters for those annual symposia. So that's pretty much my high pitch for the ARMA stuff. Now I wear the other hat, talking about the physics and the modeling of hydraulic fracturing. So this hat, where my company hat, I'm working for Aramco Americas in the upstream department. My role is looking after as technology coordinators, bridging technologies between North America and Saudi Arabia. So hydraulic fracturing has been a hot topic, is it? People talk about it all the time. So today I will give brief one slide history of hydraulic fracture models. Then we're going to look at the physics and models in several categories. For any hydraulic fracturing, you have to have rock, right? So that's number one. We deal with rock properties. We deal with brittleness versus ductile, a very controversial term. Then we deal with the stress. And stress can be isotropic, can be anisotropic stress. It can be barriers, stress barriers. Then hydraulic fracturing has to have fluid. You have to have fluid. So we're going to talk about fluid. And nowadays, with geothermal, especially enhanced geothermal system, we are talking about the thermal effect, as well as a poroelastic effect, as well as many of you probably be familiar with. Hydraulic fracturing, especially in unconventional, has everything to do with natural fractures. The success of that unconventional development fundamentally lying in the interaction between the natural fracture and the hydraulic fractures. Last but not least, nowadays people do infill drilling and refracturing. So that has everything to do with interference. So those 7 categories are what I talk about physics of hydraulic fracturing. Those are fundamentals of how a hydraulic fracture, whatever it behaves, so it evolves, so challenges are based on. So today we're going to discuss them, but the best way to discuss them is through examples. So I'm thinking that to showcase one efforts we have done at ARMA through Technical Committee on Hydraulic Fracturing, which is basically a benchmark of the hydraulic fracture models that was done a few years ago. And hydraulic fracturing models in terms of the history, we can categorize them probably in 3 groups, if you will. The first one is legacy models. Yeah, everybody knows those legacy models, GDK, PKN, in 1960s. Believe it or not, we still use them, even today. Then in 1980s, people realized the limitation of those legacy models and start developing additional features to accommodate additional physics that include, for instance, anisotropic rock, including stress barrier, anisotropic heterogeneous stress, as well as elasticity and plasticity of the rock. Thanks shale revolution or whatever you call it, the unconventional development, the hydraulic fracturing has welcomed, I call shale generation. It's like a millennium generation, if you will, that can describe and capture the physics such as power and the thermal effect of hydraulic fracturing, as well as complex fluid with the propellant, and non-Newtonian, and the natural fractures, as well as stress and fracture interference. So this is a history of hydraulic fracture models, and people have done consistently fantastic jobs and devoted a ton of efforts. Many of the folks in the audience suspended their life actually on this significant arena. So to demonstrate all the physics in 15 minutes is a tremendous amount of challenge. Pardon me. Excuse me. So I use this hydraulic fracture model runoff, as I mentioned, that was done a few years back at hydraulic fracturing community to compare different models. But the goal is very clear. The goal is to demonstrate the model validity and diversity to capture, recognize the physics we have been talking about. But the goal has never been to show which model is better, which model is best. If you have that question in your mind, then you went to you're probably in the wrong room, presentation room. So this presentation is all about the physics of different models. Blessed with this diverse community and the deep knowledge base the members represent, we have had 16 organizations with 20 models participated this effort. That's a blessing. And those are the details. And I will go through pretty quickly, but you can always find the references, the details in the references that available through these two papers. I will provide the reference too after this. So for each model, we have 20 models, right? For each model, we ask the modelers using the same input as well as have the same output. Therefore, apple to apple, right? So we compare apple to apple. To make sure the model cover all the physics, we design 7 different cases, as you can see, that each case corresponding to one physics that I mentioned at the beginning. And this different modelers choose different cases at their own view. They decide which case they participate. However, we provide the model inputs. For instance, in the case 1, single frac in elastic rock case, and we divided this category into 5 sub-cases. That's why you have so many cases to test out for all the modelers. In 6 months, if you think about it, 6 months volunteer efforts from those modelers. And those, for instance, the sub-cases can be, as many of you probably familiar, hydraulic fracturing can be in different domains. Can be, for instance, tip dominated, or viscosity dominated, or with high leak-off or low leak-off, and those different combinations of different dominance from the physics. Okay, so each case we provide parameters for the modelers to use as their input. Then we ask them to output the same. The 3 parameters we ask them to output is number 1 is a half length of the fracture prediction, and the number 2 is height, number 3 is pressure. And this comparison of the models participated in the case 1 study. As you can see, the model is quite diverse, right? So basically, you can look at the 2 groups right away. Apparently, the model uses different assumptions for their leak-off, where the fluid goes into the formation when you pump. So when you have a high leak-off, 3D leak-off case, then you have less fracture, smaller fracture length comparing to the traditional 2D Likov Cutter's Likov coefficient. So, but the general trend, you see the general trends are captured very well and consistent across all the models participated in this case. So that's what we are looking for. The general trend are well captured by all models with a difference of the magnitude because assumptions of each model has made. In the second case, we look at the stress barrier. When you have high and low stress between the formations, then the fracture has been contained between the layers with the proppant settled down at the bottom. We asked them to input the similars, and again, you see the models can be quite different. We are literally talking about the 2 or 3 times difference in fracture, predicted fracture length and fracture height. In this case, interestingly, we have one outliers, if you will, from the rest of the models, which has turned out it's not the model was quite different, but also the modeler came back to us, said that the post-processing of the results has he made one of the mistakes. So it's supposed to be opposite and supposed to follow the trend rather than do the opposite. But this is why we do this, right? So when you compare different models, that's when you find out some of the models may have some hiccups. I use another case for the natural fractures. When you have natural fractures, in this case, 2 natural fractures that cut through an injected valve, then the fracture will interact with these natural fractures depending on angle of the fault as well as the stress contrast across these discontinuities of natural fractures. And people also predicted the macroseismic distribution based on these interactions, as well as the failure mode of the natural fractures. And also another model, they can predict, for instance, stimulated the reservoir volume, which highlighted in the color through this interaction between the natural fracture and hydraulic fractures. Those models compared in those outputs, as I mentioned, the half-length. In this case, we also asked them to predict the width of the fracture and height and pressure. As you can see, again, all the models participating in this case captured the trend, but their magnitude are different. In the last case, we asked them to look at the interactions between the hydraulic fracture. We have multi-stage hydraulic fracturing, as well as multi-well. So this is the interesting case. This is the most complicated case of all the 7 cases. However, if you look at the results, for the most complicated case, the models who participated in this case actually quite agree with each other well. Agree each other much better than the other cases. That's an opposite surprise to our expectations. In the last, okay, those are showing different models for different physics, right? So as I mentioned at the very beginning, it's not about model superiority. It's about model relevance. So what the problem you are studying, and you pick up the right model for that study. As an example, for instance, in this study, I'm looking at the perforation effect of hydraulic fracturing. So those are the different perforations. You can change perforation orientation, perforation depth, penetration depth, as well as density, how many perforation holes you want to have in the segment of the pipe. So those parameters are studied with respect to the breakdown pressure as well as the fracture geometry created by these perforations. This is one of the example when you have, for instance, 12 shot per foot, which means you have 12 holes in 1 foot of pipe casing versus a 6 foot. 6 foot is half of the perforation. The fracture grows pretty marvelous, I would say. For instance, in this case, there are only 2 fractures grew out of 12 holes. All the rest of the hole being linked by the longitudinal fractures instead of transverse fractures. That's very interesting, isn't it? And compared to 6 shot per foot, less dense, sparse perforations, and the geometry you created from the hydraulic fracturing are significantly different. When you plot all the rest 5 cases, each perforation design has resulted in different fracture shapes, fracture geometries, and each of them going to have different pressure responses in terms of breakdown pressure. So this plot will shows that how much difference each perforation can make to reduce or increase the breakdown pressure to initiate hydraulic fractures. And we clearly have a winner if looking at the minimum breakdown pressure. Then you should go single perforation and deep penetration. You don't need to go. In our case, we went all the way to 50 inches, but the key is to go deep. Okay, so that's actually a direct recommendation to completion engineer. Hey, rather than do 12 foot shot per foot, let's do 1 shot per foot. You actually might be reducing your breakdown pressure. Why this hydraulic fracturing model is so important in this process? Not only make recommendations in completion design, but also look at what's after hydraulic fracturing. In this case, the light area you can see as stimulated volume. Okay, that's where the oil or gas will produce from. And in 2 perforation cases, as you see here, fracture started turning away, but you create this stimulated volume around the fractures. Why these 2 fractures behave like this has everything to do with the stress. That's the beauty of geomechanics. So the stress prohibit the growth of one fracture and encourage the other to go bigger. That's how this developed. And this is a 2 shot. And compared to 1 shot, there is a quite big difference. You have bigger stimulated volume and you have larger area. With the less shot, spend less money, you have bigger stimulated volume. So that's why I think it's better off. So that's the example, right? Instead of to ask a question, which model is best? You pick up the model fit for purpose, fit for your study. As the last slide, this is my email. Feel free to send me email or any questions. I will share the reference, as I mentioned. A lot of details, they all are in the details. I will provide references for you to read the details. By the way, this is the book that Annie mentioned to be introduced me. We had a lot of fun at that time at the Jet Propulsion Laboratory when I was working in Los Angeles. The project we are working on as a rock mechanics guy, okay? As a rock mechanics guy is called the Martian Deep Drilling Project. We try to develop a drill on the Mars that penetrate up to 1 kilometer of rock, of basalt rock, okay? That's probably one potential career path for some of you in the future. to help this not only drilling break the rock on the Earth, but also break our Earth on other planet. With that, I'm more than glad to answer any questions. Ali, feel free to take over. Thank you for your attention.
Well, I guess thank you again for giving us your time and your knowledge in hydraulic fracturing and rock mechanics. And it's definitely like I think people are now trying to go for like what they call like exotic rocks, which is like just not here but everywhere, which is a new realm for people who are interested into like going further or like broadening their expertise. So I do have a couple of questions, and one of them you really touched on, which is the importance of modeling what you're after. And if you can give us some more insight on that, because you see people who start off with like such a very complex model when the problem at hand is so small, and the other way around. So if you could give us some more insight on that.
That's a fantastic question. I am very, actually, a lot of work people have done, including, especially in terms of understanding the physics, including many work that Professor Giovanni and folks in University of Toronto and other universities in Canada and all over the world are trying to capture the physics. There are so many physics, right? There are many physics. But fundamentally, you need to capture the key physics that matters most for your applications. In our case, for instance, I use the perforation design as one of the project I had an opportunity to work on. So is the plasticity important in that case? Probably not as important as, for instance, the rock anisotropic or interaction with different layers, especially the either wood, not necessarily natural fractures, but I call mechanical discontinuity. So yes. So that's why you need to figure out which physics is most important to you, and then choose the model that has captured that physics. That's why it is so important, especially for rock mechanics guy, to read not only the application papers, but also the fundamentals of those models, how those modelers develop their models, understand their assumptions and simplifications. That make a big difference between the rock mechanics guy and the completion guy.
Fair enough.
All right, so that's make Earth unique.
That's true.
Thanks. So, that's a very good question.
Yeah, but that will lead me to the next one, which is, what do you think currently is the biggest challenge when modeling hydraulic fracturing, especially when you consider exactly what you said, which is the mechanical fractures, and if you have some existing discontinuities, and how, like, so the first question is, what is the most important aspect or challenge? And then the next one is, how do you foresee how these fractures interact?
Yeah, I'm very glad, actually. Those are questions from students. Professor Giovanni, you should be very proud of your students. I have to say, it is a fantastic question. I'm so thrilled. This is a make me feel very. I can clearly see future of rock mechanics, not only hydraulic fracturing. Feel very comfortable. To answer your question, Ali, I keep thinking these models that used to be seen as famous saying, all models are wrong, some are useful, right? So we have 20 models I showed in this exercise, but we have more beyond the 20s in the community, from the community. So always, where is the end? Where we go? From my perspective, I only speaking from my industry perspective. Of course, you have academic interest in many different aspects of hydraulic fracturing. imagine one day probably people even talk about the fracturing on the Mars. As a matter of fact, if the primary drill methodology we propose to JPL is actually based on the fracture mechanics, not based on the based on the grinding or other things. But on the other hand, what industry needs is probably, I think, from the capture physics point of view, we have done a fantastic job. But from application point of view, but physics is so complicated. We have been constantly challenged by so many field observations, including most recent call-through project. For many of you are familiar with, if not yet, I strongly encourage you to look up the call-through project managed by GTI, Gas Technology Institute, sponsored by DOE from Permian Basin. And this oncoming URTeC conference, they have 10 papers actually, presentations over there. So they drill the hole, they fracture, they call back, they take a look at what fracture look like. And guess what? It's so full of surprises that the challenge the modelers all the way through. It turns out there are so many fracture branches, if you will, along near wellbore that is beyond what current fracture models have predicted. Then after that event, there are a lot of activities development from the modelers with various physics included to accommodate this multi-brand fractures that one way or the other seems fit the puzzles together. But having said that, we need to be humble. We need to be what do you see? In front of the mother of nature. It's just amazing, and that's why people from the university, especially with the equipment, control the environment, look at all those fundamentals. It is very, very important. Eventually, at the end of the day, when you apply the field, you need to figure out the number one rule is whether the model can be useful, not necessarily whether the model can capture everything. Okay, so that's
the key, right?
Yeah, the thumb of the rule.
So I will add to that. So we actually conducted true triaxial hydraulic fracturing experiments on shale, and like you said, with the coring back experiments, the results that we have are nowhere near what we thought we would have. So
your experimental apparatus, that true triaxial that Professor Giovanni lab has been managing, has been running, is truly one of the kind. I have to say, I kind of jealous you guys can put your hands on that state-of-art equipment. And I have to say, the true in situ stress, it is a luxury to be able to capture it at a lab. Fantastic job.
True. So we actually have a question from Energy Simulation, Andrew Settle. Just need to find him so we can unmute him. Yeah. Andrew, I think you're unmuted. You can go ahead.
Okay. Wow. It's a wonderful, excellent presentation. I'm really happy to hear that you'll be the incoming president for ARMA. So I'm going to ask a philosophical question. I just attended a virtual session from the World Geothermal Congress yesterday, and a lot on reservoir engineering. As you understand, they talk about fracturing, hydraulic fracturing for enhanced geothermal systems. And I'm not too sure that some of these people who may not have the background in petroleum engineering, maybe civil engineering, but that combination with the expertise that we have developed in oil and gas, and especially from what you've done and what I've seen today, that they could really use the expertise other than we need to look at igneous rocks, metamorphic rocks, supercritical and super hot fluids and rock interaction. So going forward, in terms of expanding the scope of ARMA, if you haven't been doing that already, would you be kind of talking to SPs, talking to the geothermal guys, and actually expand the expertise and help those guys out, so to speak, and not to mention expanding the potential job opportunities for graduates from rock mechanics or soil mechanics engineers?
I'm so glad, Andrew, you asked the question. The question has a lot of implications, not only for the career paths for the students and for the career rock jockeys, but also as a society, how we adapt and how we support this low carbon era. In this low carbon era, there are multiple fronts, Andrew, as you pointed out. You probably many of you been participating as well. So, for instance, today, right before our meeting, DOE Geothermal Technology Office Manager Lauren Boyd gave a seminar on EGS, Enhanced Geothermal System, and to the hydraulic fracturing community. This hydraulic fracturing community has more than 1,000 members, led by the technical committee, about 50 members. And half of the technical committee on hydraulic fracturing are actually active in geothermal. So half of from petroleum background, half of them from geothermal background. Now background, the field actually active in those fields. From hydraulic fracturing community point of view, we are actively bridging these two fields together. In 2 years ago, before the pandemic, we actually held the first conference with the petroleum and the geothermal together in Beijing.
Wow.
The first international geothermal workshop in Beijing to bring the two audiences together and talk to each other. It was for petroleum engineers sitting in the room for 3 days, understanding or listening. The geothermal folks is a tremendously both educational and enlightening, and as well as inspiring too. So I couldn't agree more with you, Andrew, on this. And for ARMA this year, the annual symposium, we created the 6th independent technical track. Over the past week at ARMA, we have a technical track at the symposium. We have technical track of petroleum, mining, civil, and interdiscipline, 4 technical tracks. And this year we created the 5th. It's called the geothermal. So the geothermal become independent technical track at ARMA Annual Conference. And it's going forward. You're going to see that next year in Santa Fe, the annual conference. Actually, the Santa Fe conference is chaired by a geothermal technology office DOE manager. So you're going to see a lot of geothermal activities. Yeah, that Blankenship.
What about one other kind of side question is the carbon capture and utilization storage side of things. I think there's a lot of geomechanics and rock, that could be involved as well.
Exactly. As a matter of fact, our newest technical committee, I mentioned the 6th technical committee. Besides technical committee on hydraulic fracturing, the newest one is called the underground storage and the utilization. So the CO2 sequestration is one independent domain under that technical committee, and very active too. They have a monthly seminar to put together different CO2 sequestration and underground hydrogen, for instance, other storage and utilization applications tied to the rock mechanics. So Andrew, I strongly send me email. I strongly suggest you get in touch with those technical committees, and we need your help. We need your help to participate and also help to suggest how, as a society, to support those efforts.
Good. I'll need your email address later.
Sure.
Thank you.
Yeah, I'll put you in contact. There's no problem.
All right. Thank you.
So we have a question from the audience, and it's something you had alluded to, which is, what is the importance of? Oh, thank you. There you go.
Yeah, I put my email address here.
Yeah. It's easier. So, what is the importance of the intermediate stress in 3D models? Like, it was very nice. You showed a lot of 3D models, but some people still revert to 2D. So, what is the importance or the influence of the 3D intermediate stress?
The people who ask this question know more than I do.
Fair enough. That was a very good answer.
And any people in your lab, in Professor Giovanni's lab, knows more than I do. And the intermediate stress is actually, as a matter of fact, probably I would expand this question, not only the intermediate stress magnitude, but also in many of the cases, if you look around, especially in the infield drilling right now, in many of the infield drilling with the reservoir depletion has been done, and this intermediate stress can change. Not only necessarily in some of the cases, especially when you have the strike-slip stress regime, not necessarily vertical stress become the intermediate stress, and because of the stress disturbance by the depletion, by the injection, by whatever you have done on the whole. And if you look at the longitudinal fracture development along the valve, near valve, during the hydraulic fracturing injection process, the main reason they develop this is because of stress change. The stress is no longer follow the far field in situ stress, but also develop its own stress regime around the individual valve and perforations. So that's why I make this question so important, and that's why I make your lab is the envy of many rock mechanics guys like myself. There are very few labs in the world can do this. Okay, so whatever come out of your lab, has already actually made a significant impact in the community, but also the work that coming for in the future will continue have that significant impact as well.
Hopefully, thank you for that. So one last question before we let you be. So there was a question from Ms. Yu Wang. Just need to unmute her.
Yeah, for the rest of folks, even though the time may be limited, I will be around after this, if it's okay with you, Ali, for 5 or 10 minutes. Since I'm on vacation, actually, I at all.
We're more than
feel free. Yeah, I love to chat with the students, especially I want to hear for the student organizers. You're more than welcome to stay a little bit longer. I want to hear what you want. Okay, after this.
Sure.
Hello, Dr. Han. Thanks for the informative presentation. I do have a question for you. So I'm working on studying the impact of the complex fracture geometry from hydraulic fracturing on the production afterwards. So when I'm predicting the production enhancement, I have a problem on predicting the far field stress effect in the long term. Do you have any suggestion or comments on that?
By far field stress impact.
Yeah, on the production for the shell.
Can you elaborate a little more? What do you mean by far field stress?
Like in the field, the after hydraulic fracturing, the production would increase immediately, right? Because of the increased permeability.
Yeah.
But when I'm doing the modeling, for example, using a commercial software like CMG, when I model it, I only consider short-term production effect, like for example, 30 days or a month, and the boundary condition is set to a fixed pressure initially. Yeah, but with the production decline, well, in the reservoir, I think there is far-field stress effect. I'm not quite sure how to handle that. Yeah.
Excellent question. This is for the real case study. As a matter of fact, I share the pen with you.
Excellent. Thank you.
We also face similar challenges as well. As a matter of fact, not only we, but also many other operators. So that's where the beauty of the geomechanics comes from. For all the young, early career professionals, folks, you will have splendid future. Mainly because we are small, but we are interdisciplinary. By that, I mean, we can study near available as the case I showed you. Yeah. We also can study the reservoir at the reservoir scale and even the basin scale. Yeah. The question that you ask is the reservoir scale depletion effect on the in situ stress, therefore on the fracture productivity over the time. And this area, you need a probably different model from, for instance, my case study for the near available. But the model that you pick needs to capture what your main concern is, which is depletion related reservoir behavior. So in my practice, normally, here is what I do. I understand the challenges, especially associated with how many mini cells you can run with natural fracture, the small elements, and then you have big reservoir with upper and lower burdens. So in my case, actually, I normally, if I face this challenge, I will look at this reservoir depletion as one case.
Okay.
Without these small fractures, but with production profiles, as if you have this well pool there, and you have big fractures that drain the reservoir at the same production rate as others, and then you simulate the stress profiles over time. Then apply that stress profile, output that stress profile, apply to your this previous model has the fracture and all the near available features in it. Then you have the time sequence of fracture stress profiles in it already. Ideally, the best case will be find a coupled reservoir geomechanics fracture model altogether. Over the past, it was limited, but right now I think there are some models can reach that stage because of the cloud computation.
Yeah, that's a high computation demand.
You betcha.
Well,
good question. Good question. Good luck as well. You touched the essence of what Ellie's question earlier asked. That what model can be useful. Yeah.
Thank you.
So I actually don't see any more questions in the chat. So maybe with this we could end it, and I'll ask Dr. Han and all the committee to stay back. And for everyone else, thank you so much for attending, and we hope to see you in our upcoming events.
Thank you all for your time and great questions. And I hope one day we can see each other in person. I hope that coming very soon. And thank you all. Have a great weekend too.